Okay, welcome to this course, and you know what it is: adaptive signal processing. It's a very enjoyable course, and through this course you will learn many things which are actually useful in several other subjects, in communication, signal processing, image processing, machine learning, deep learning, what not. So, I presume towards the end of this course we will really be satisfied with lot of useful knowledge. Okay, my name is M. Chakraborty, Professor Mrityunjay Chakraborty, Head of Electronics and Electrical Communication Engineering at IIT Kharagpur. So, I will be pleased to bring to you this interesting topic, adaptive signal processing. Now, core of the adaptive signal processing is actually adaptive filter. So, development of adaptive filter and its application, that actually constitutes the story of adaptive signal processing. Now, what is adaptive filter? You have done one digital signal processing course somewhere, in your previous studies, I am sure. So, you have studied FIR filters, IIR filters, and you can design them to have things like low pass filter, high pass filter, band pass filter, like that, FIR, IIR. In the case of IIR filter, you may have studied Butterworth filter, Chebyshev filter, and those kind of things. I mean, those filters are very good, but their problem is once you design, all the parameters, that is the filter coefficients, are fixed, and you construct the filter using these coefficients and use it in practice. It will work beautifully, all that is fine. But suppose the purpose, the environment in which this filter is supposed to work, or its goal, it changes after some time. No way to change the filter. You have to throw it out, you have to construct a new one. But in a case of adaptive filter, filter coefficients are not fixed. They are continuously adapted, continuously changed from clock cycle to clock cycle by some nice adaptation relation or formula called, by some training method or by some adaptation method, by some adjustment method. These are real terms which are equivalent: training, adjustment, adaptation, so that at the current moment it is doing the best job for us. Okay. So, that is the story of adaptive filter. I will consider adaptive filter applications and its general structure not at the very beginning, but maybe after some lectures. Once I cover a very basic adaptive filter called least mean square, LMS, and then I will present many applications, because then you will be able to appreciate those applications. Right now, if I bring in the applications and then bring in the theory and development and all that, algorithm development, you won't appreciate that much. So, you give me the freedom to start the way I want, that is, I will start with basics and then develop some very basic adaptive filter, and then we will put it into applications, and beautiful applications will come. But I am telling you, applications come in various contexts. Okay, communication, control, signal processing, image processing, machine learning, deep learning, even microwave engineering, so many. To give you just an idea about what is an adaptive filter, suppose you are given an analog signal X A for analog, X A T, which has a sinusoid component, okay, A cosine, some capital omega C T. Capital omega is the frequency, analog frequency, C for carrier. I am just putting it, omega C, its unit is radian per second. So, radian per second and time is second. So, second into second cancels, whole angle must be radian, you get back radian. So, radian per second is an angular frequency, analog angular frequency, maybe plus some phase phi. This is a signal, but this is suppose added with some noise, wide band noise, maybe white noise, okay, and noise power is not trivial, not small, quite significant. You want to first process it digitally, so you will sample it, maybe at sampling period equal to maybe capital T. So, nth sample of XAT will be XA at n times capital T, T, 2T, 3T, 4T like that. So, at those points we will have sample, and this I denote by Xn. So, I have Xn. So, before I do anything, I am converting into discrete time form, and then I will consider this problem, how to eliminate the noise as much as possible. Okay, so, it is A cosine omega c, n t is current time point, that is n into capital T, which is x a n t, which I call x n. So, omega c small t is, that is the time point I am taking the sample. So, x a n t maybe plus phi plus z n t. Let me put z a for analog to distinguish between analog and discrete time. All right. Then little bit of DSP we know, omega c into t, this is denoted by small omega, which is digital frequency. This is basic of DSP, basics in DSP you must be knowing, I am sure. Digital frequency, its unit is radian, radian per second, and here second, so second cancels radian. So, you can make that assumption, let me call it omega c, c for carrier. So, A cos omega c n plus phi. So, this is one discrete time sequence, cosine sequence, and this I call z n, like x a n t was called x n, z a n t is called z n. So, equivalently I have been given in discrete time domain one sequence which has a sinusoidal component which is by signal, but this is added with some good amount of noise, and this is a wideband signal. Your purpose is to filter out this noise as much as possible. So, ideally what you should do, you should design a band pass filter of frequency response like this, at this magnitude response like this, at omega c and at minus omega c you will have a pass band, very narrow pass band. Sorry, this is this did not come in the proper place. So, let me erase this. This is your omega c. Okay. So, around omega c and minus omega c there is a pass band, very narrow pass band. If you pass this signal through this cosine signal whose frequency is omega c, that will pass through. But noise, which is white noise, which is wideband noise, I mean, is spread over the entire frequency range from minus pi to pi. You know, in the DSP this is the range, and this becomes periodic. Whatever you have here, that gets repeated. So, you see from minus pi to pi. So, for the entire range, I mean, this noise will have its presence. So, filter, bandpass filter will chop off most of the noise. It will allow only the noise frequencies in this which are within the pass band. So, obviously, most of the noise power will go, and fine. So, you are happy with the signal which will go through, and very little noise will filter through this, because pass band is very narrow, and this goes on for some time. Now, suppose after some time signal omega c signal frequency omega c changes to some another frequency omega c prime, means analog signal omega c, which is capital omega c t, this changes to some new digital frequency omega c prime, which is all right. Then this will be outside the pass band, maybe omega c prime is here. So, then the signal also will be filtered out by this band pass filter, because this center frequency, the frequency of the sinusoid is outside the pass band, and I am gone. So, my filter which is working fine now, it will fail to work in future when the frequency changes. But if it is an adaptive filter, what it will do, this bandpass filter, if it is adaptive, it will not stop at this, it will continuously monitor the input data and it will track the variation of the input frequency. So, if the frequency changes, it will also change its passband by some formula, so that new passband is here. Okay. So, passband will shift. There will be an adaptation mechanism, training mechanism, adjustment mechanism by which the coefficients of the filter will change, bandpass filter, so that if the frequency changes from input frequency changes, digital frequency I mean, omega c to omega c prime, the filter band parameters also will change, so that new passband will be here and here. So, the signal again will pass through. Okay, this is a very famous example. This is called adaptive line, because if you take the frequency, I mean if you take the discrete time Fourier transform of this will have two impulses at omega c and minus omega c. Those are like lines, and this will be flat white noise. So, what this it will do? It will enhance the lines, that is signal will be enhanced or effectively noise will be reduced, and it will be done adaptively. So, this example is that of adaptive line enhancer. Alright. So, this gives you an idea about what is adaptive filter. So, there will be an adaptation mechanism that is required, because if external environment changes, like the frequency, incoming frequency changes, I should be able to process correctly. Okay. So, I should have an adjustment mechanism, adaptation mechanism by which my parameters can be changed to suit to current requirements. So, in adaptive filter there is a filtering part, in parallel there is an adaptation part. All right. So, there is actually a filtering part and there is an adaptation part. So, there is an adaptation algorithm which works on the filter coefficients and adjusts. So, symbolically or schematically we show like this: tuning. So, at every clock it is calculating new parameters for the filter and changing. So, that change is indicated by this. And adaptation algorithm requires input information also, output information also. Okay. This is the typical structure of adaptive filter, both the filtered part and adaptation part. So, adaptation part is what is our target. There are two very famous class of adaptive filter algorithms. One is called least mean square LMS, another is recursive least squares RLS. Right. We will study these and these, but again we will just give an introduction, because this is a very huge topic. Many algorithms under each of them each category have come up, their analysis is quite involved and all that. So, we will not be able to cover all, but my purpose is to introduce you to these two, and through that journey also make you knowledgeable about many related things which you find useful in other subjects like signal processing, image processing, communication, as I told, deep learning, machine learning and all that. All right. There are many books available. One is adaptive filter. I cannot remember the exact title, whether it is Introduction to Adaptive Filter or Adaptive Filter Theory and Practice and all kind of things, but essentially the adaptive filter. This is by no other person that good old Simon Hekin. I think it is a Wiley book, Wiley Stern, available in India. Another is a more involved book by Ali H. Said. It is again Wiley, InterScience, New York. Available in internet, I think. New York. There is another book of mine, which I like, Adaptive Filter, by an ex-Iranian friend of mine. His name is B. Farhang Boroujeni. Print is all. But apart from this, please see my video lectures related. You will find some useful information here. But most importantly, it is very important in any of my subjects that I teach to attend to my lectures and understand there, because many things I say in the class which are not found in any of the books. Okay, they are very useful. All right. Now, so how to go about the subject? The basis of this subject is, two things. One is probability and random variables, because the signals that we come across, they are random in nature. Okay. So, how to characterize them and all, some basic properties and features and all you have to study, like probability density of one variable, two variable, multiple variable, correlation matrix, covariance matrix, their properties, all those. Okay. Random process, these things I will cover, I will take quite some time. Then I will go to what is called optimum filter, and then make it adaptive filter by LMS, and then I will take up the applications. I will show many examples. Then I will come back, I will do some analysis of the LMS algorithm, that it should finally converge to the best filter. The adaptation should take you to the best filter, and then I will take another category which is recursive least squares. Again, there are many. I will take the very basic one. So that will be the flow of this course, roughly 20 lectures, but I think this is a very good foundation for many related subjects, including even neural network. Neural network also is a kind of adaptive filter. Only thing is, in adaptive filter, input is a sequence, time sequence comes in time. In neural network, we also have filtering kind of thing, linear combination. We also have adaptation or training, but input is not a time sequence. Input is just a stationary data, a block. Okay, difference, but many things are common between the two. So, with that background, I then start basic probability and random variables. Okay. We will consider real and continuous random variables. Okay. Real and continuous, like suppose you are measuring the temperature, daytime temperature, call it T. So, T will take real value, it cannot be complex, but T is not fixed. Any time in anywhere, any part of the city, or any time, during the day and night, it will have fluctuating values, okay, different values. So, it is random, it is real because it is not complex, and also it is not discrete. It is not that temperature will be either 30 degree or 31 or 32, it can be anything. So, on a real axis, if it is a real axis, suppose the origin 0 degree is here, it is continuous. It can be here, 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 anywhere. It is not discrete. That it will be either 1 degree or 2 degree or 3 degree. Okay, it can be. So, this kind of random variables are called continuous and of course real random variable. More formally, whenever I say there is a random variable, real, continuous, any random variable, it means along with the random variable, say x, we denote the variable by capital letter x. Always there is an experiment or trial or observation process, okay, by which we observe the value of this, like we measure using a thermometer the temperature and find a value. So, that moment whatever be the value you get, you assign that value to this. So, there is always in the background an observation or experiment, a notion of experiment or trial or observation along with a random variable. That is, it is not fixed every time I observe, okay, or I experiment and find a value, give it to this. So, its value changes, fluctuates experiment to experiment, but there is an experiment or observation trial, that notion of that goes with that. And if it is continuous real, then it will take in all experiments real values only, not complex, and if it is continuous, the values will be continuous on the real axis. It will not be taking specific discrete values, that is the only thing. Alright. This is the meaning of random variable, continuous real random variable. Now, suppose this is my real axis, this is the origin, capital X will take any value. I mean, it is not necessary that it will take all the values from minus infinity to infinity, it may be concentrated in certain zone. For instance, if you are measuring temperature, it can be from maybe 10 degrees centigrade to 40 degrees centigrade, it cannot be 1000 degrees centigrade. So, whenever you measure, your measured values will may be concentrated in some zone, but they will be real and they will be continuous, they will not take pre-specified discrete values only, they are continuously on this axis. Okay. So, suppose capital X, now I want to find out probability, I have to define probability. So, suppose I have a position some small x, this much value, and small x to some small portion dx I take. So, x to x plus dx, and dx is very small. Then the probability that capital X in my experiments will fall here, that is probability that capital X will be less than equal to this point, greater than equal to this point. That should be proportional to this width, because if it is larger, obviously chances will go up of capital X falling here. If it is smaller, so it will be smaller. So, as long as dx is very small, I can say this probability is linearly proportional to this width dx. So, it is proportional to dx. That means, it will be equal to some proportionality constant times dx. So, that proportionality constant I denote by p, and I put a subscript capital X because my random variable is capital X, not capital Y or Z, because there may be a situation where I may have so many random variables, capital X, capital Y, capital Z. To distinguish between them, I put a subscript. Not only at dx, this is the proportionality constant, okay. But not only that, this px will depend on where this slot is located, that is at point x, because if I now take here the same dx, the probability of capital X falling here may not be same as this. It will depend on, like as I told you, daytime temperature, maybe it is concentrated between 10 degree to 40 degree. If it is 100 degree, so obviously there will be hardly any chance. Okay. Which means probability of capital X falling in a slot like this will depend on where this slot is located, here or here or here or here or here. So, this is located at the coordinate x. So, this will be, this proportionality constant will vary, it will be linearly proportional to dx, but proportionality constant cannot be same, it will be change depending on where is this slot located. Okay. So, it will be a function of small x. Okay. This is the proportionality constant, and that is called probability density function of x. All right. Therefore, probability of capital X falling between two points, some x2, x1. That will be what? That is, suppose I got x, this is 0, this much is x1, this much is x2. So, probability of the capital X will be here, will be what? I have to sum up the probability in this slot, in this slot, in this slot, each of widths dx. So, probability of capital X falling in this slot of width dx, in this slot of width dx, again in this and so on. So, I have to add. Since dx is infinitely small, this total probability will be nothing but integral. It will not be a discrete summation, it will be integral. That you know, integral has a definite integral has a limit of a sum. If dx is very small and goes to 0, this summation will go to become an integral. So, this will be nothing but this thing summed, but summation will not be discrete sum, will now be this is the probability. Therefore, a question comes, probability of capital X taking value from plus infinity, that is the extreme point to the right, to the extreme point to the left, minus infinity. That will be just this, you put change the limits. But you understand, in every experiment capital X will definitely take a value from minus infinity to infinity. So, that is an event called certainty. That is, an event is bound to occur. There is capital X taking value from minus infinity to infinity in each trial. So, probability of that is this. So, this is nothing but probability of certainty. Now, certainty is a global event, global parameter. Sun rises in east, this is certainty. All human beings will die, certainty. All human beings were born one day, certainty. So, they are basically same event. They are manifesting in different forms, but they basically mean the same thing, that is certainty. That is something that is certain to happen. So, certainty will have a constant, will have a fixed probability, whether sun rises in the east, probability of that, or all human beings will die, probability of that, basically probability of only same event, that is certainty. That is something which is certain to occur. So, that is basically a constant, independent of whether I am talking in terms of sun or in terms of human beings dying, certainty. So, this is nothing but probability of certainty, and that we can take to be a, we can normalize to a value of our choice. This is probability of certainty, which we normalize to be 1. You could have taken 100 also, does not matter, but globally it is taken to be 1. That certainty is an event which will always occur, and we take its probability to be 1, which means this integral, when minus infinity is here and plus infinity here, which is the probability of capital X falling from minus x to x, that is equal to 1, that we take. All right. Now, suppose you are given, I am writing here. Now, suppose given a function f of capital X. Capital X is the variable, small x is the actual value, okay, f of x. Now, every time capital X you find out by an experiment, you plug in the value here, you get something. Next time another capital X, plug in here, you get something. So, this function also is random, its value changes, fluctuates randomly depending on experiment to experiment to experiment. So, what is the average value of this function? Average value means capital X falling here. Okay, consider this slot. The dx is so small, whether capital X is here or here or here or here or here, dx is small. So, I will assume it will take a constant value f at the boundary, whatever be the value, same value whether I am here, here, because dx is infinitely small. So, function does not change much, hardly changes. So, function value at that point which is small x, okay, that point which is small x, that value will continue inside also. Okay, that is the thing. But that will not always occur. It is not that whenever I measure capital X, I will get this. I will get this with a chance. So, what I do? I multiply by a chance factor. So, if the chance probability of capital X falling here is high, value will be, this will be multiplied by a weight appropriately high. That is that this value will occur with more power. If the chance of capital X falling here is very less, then the chance factor which is this, that probability of capital X falling here, that will be less. So, I will be multiplying this by this. So, its value will go down because chances are less. Okay. So, I will be applying a weight factor, multiplication factor on this, which is the chance factor. Okay. The chance of having this value f of this much small x, which is same as whatever we have inside. Okay. Let me go to the next page. I draw again. This much is your x. So, this width is dx. Okay. Function is fx, f capital X. The f capital X takes the same value f of small x whether here or here or here or here, because dx is so small, its value does not change. So, when I conduct an experiment, I observe capital X, so I find out f of capital X. So, that will be equal to this value with a chance. What is the chance? Chance factor was this much, that is the chance of capital X falling here. So, the value will not be this, because I am not certain that I will get this. So, I have to multiply by the chance, I have to use weighting. I have to weight this by a chance factor. So, I weight this by a chance factor. Then again you can take next lot. Again f of x falling, taking value from here, it will be multiplied by another chance factor, f of and it will go on. So, if I want to take a weighted average, this function into weight, again another value into weight, and if I add them, basically this will be integral, because dx is infinitely small. So, if I add them, what I am doing is actually, you can understand one thing. Suppose I gave you some variables x1, x2, or maybe not x1. I gave you some values, maybe y1, y2, y say n, and I have scalars. C1 is a scalar number, C2 is a scalar, Cn is a scalar. So, I multiply y1 by C1, weighting, using a weighting factor on y1 by C1, then C2 y2, Cn yn, and then divide by C1 plus C2 plus dot dot Cn. This is called weighted average. All of us know this. So, it was discrete, same thing I am doing. I am taking this function multiplying by a weight factor, and this I am doing over all the slots. So, I am adding here, adding here it was a discrete sum, here is an integral. So, I am adding. So, it will be divided by sum of the weights are these weighting factors. It was discrete sum, now it is continuous sum. Okay. So, this is a weighted average or expected value of this, but this we have seen, this is equal to 1, we have seen in the previous page, because this is the probability of certainty, that is 1. So, this entire thing we denote by E of f x Again I put a capital X here because I may have many random variables, capital X, capital Y, capital Z and all that, to distinguish. There is an alignment problem here. So, expected value, average value, it is a weighted average, that will be same as, because this is 1, so it will turn out to be this. Here you put small x, integral variable, all right. So, this is called expected value, expectation, expected value of f x, average value, all right. Example 1, suppose f x is x itself, very simple function, f x is nothing but x itself. Then E x, f x is x, so we put x here, that will be what? F x, f small x, so this was capital X, so it is f small x, integral will be f capital X is capital X, so f small x is x and this remains as it is. So, x multiplied by this probability thing, chance factor, integral, and that is called the mean, because expected value of the random variable, that is mean. You can denote it as mu of random variable x, so mu x, all right. Then another function can be f of x is x minus that mu I found out, that is a constant now. So, put that mu x and square, this is another function. So, here expected value will be f of small x, so it will be small x minus mu x, okay, whole square, that is the function, times this. This is called variance and denoted by sigma square. You can put x to indicate random variable x. What it means? That mu was the mean, this is mu x, and around that I have fluctuations. So, capital X can be here, maybe here, maybe here, maybe here, in experiment to experiment. So, I am finding out the value minus the mean, this much is the increment, this much is the increment, this much is the increment, okay. I am squaring them up. So, even if it is positive, square up positive, even if it is negative, squaring up positive. So, every incremental part, I am taking the power means I am squaring, okay, and then average, because I am multiplying by the chance factor and integrating. So, it is the average power of the incremental part, okay, like it is a DC. So, if you take the waveform minus the DC, so that will be AC, fluctuating around the origin. So, then you square up average, that is what it is. So, basically average AC power is called variance, all right. Now, I consider joint random variable. Suppose I have got two random variables x, y, okay, both continuous and real. Like suppose you are measuring temperature, which may be capital X, and humidity, which is y. Now, temperature, humidity, I do not know whether there is any formula relating them, but at least we understand that there is some kind of relation between them. Temperature, they are all about atmosphere. So, one influences the other and vice versa. How and all we do not know, but temperature, humidity. So, every time I conduct an experiment, I observe not just one variable here, I measure two, and these two have an internal relation between them. One is temperature, which is x, another is humidity, y. Both are real because they cannot be complex, both are continuous, they cannot be discrete, that humidity is either this or that or that. So, both are, they may be concentrated in some area on the real axis. So, in every experiment I measure a pair. Therefore, now instead of one real axis which is for x, I will have 2, alright. And now I want to come to again similar notion of probability density, not of one but of two variables jointly. They are called jointly random variable. Okay. So, I go to x and then this much is suppose dx, and here again I go up to 1 and suppose this much is dy. So, this point is x and y. So, its coordinate is x, y, this point, and this point is x plus dx, y plus dy. All right. So, every time I conduct the experiment, capital X and capital Y together may fall within this box, that is capital X may lie between x to x plus dx, simultaneously capital Y may lie between y to y plus dy or may not, okay, because they are random. So, if they lie, if capital X lies between x and x plus dx simultaneously with capital Y between small y to y plus dy, that means the pair lies here, okay, in this small box. So, the probability that the pair k x comma y will lie within this box will be linearly proportional to the area of the box, because area is larger means my chance will go up, area smaller means chance will go down. As long as the area is very small, I can assume it to be linearly proportional. So, probability of capital X lying between x plus dx to x simultaneously with, simultaneously is very important, that is why they are joined, with capital Y that will be linearly proportional to area, area is dx dy. So, equal to a proportionality constant. So, I put capital X and Y here to indicate which random variables are important, are present, constant dx dy. Now, this constant will depend on the location of the slot, because if the location is somewhere here, same dx dy, but there is no guarantee this probability will be same here also, because it is quite likely, it may be likely that I mean more often you will have temperature in this zone and humidity in this zone, hardly ever here. So, obviously, the two probabilities will not same. So, dx dy is same. So, proportionality constant will vary. So, that will depend on where this is located. It is located at x y. Okay. So, it will be a function of, and this thing is called joint probability density. So, if somebody asks you in an interview what is probability density, you have to give the entire background, like if it is just only one, okay. If it is only one, you have to draw this line, draw up to x, then x plus dx, then tell that probability of capital X falling here will be linearly proportional to this. then the proportionality constant, okay, that will be your this thing, probability density. Yes, you have to draw this line, then you have to define that this is linearly proportional to dx, then the constant which is a function of the location of the slot, that is called probability density. Its integral will be 1. All those things you have to tell. All right. Now, after this, so certain things will follow very simply. Probability, just generalization from the previous example, probability of capital X lying between x2 to x1, simultaneously y lying between y2 to y1. This is nothing but I have to integrate this over that zone. Small x, small y, dx, dy, now double integral from x1 to x2, from y1 to y2. And clearly, from minus infinity to infinity, if I do this, again that is the probability of certainty, because the probability of capital X y lying on this entire plane, there is capital X from minus infinity to infinity and simultaneously capital Y from minus infinity to infinity. That will always happen. So, probability of that is given by this formula. So, there is again the same event which is your probability of certainty, all right, probability of certainty, but that is constant, that is global, that is always 1. So, this will be 1. Okay. So, this much is for this lecture. In the next lecture, I will again proceed the same way. I will assume that given a function f x comma y now, earlier it was f x, now f x capital X comma capital Y. Okay, what will be the expected value of that, and then I will take some cases of that, and then I will go to something very related and useful called conditional probability density. All right. So, I stop here now and we meet next time. Thank you.